Oh yeah, just had me a little bit of brewer's coffee. Before I do Unit 6, Day 1, Logarithms and Exponents, I definitely need coffee. The major reason why I need coffee is because on Tuesday, when I get into class, I'm going to have to listen to Mr. Krause, when am I ever going to need this stuff? Why would I ever want to learn about logarithms and exponential functions? Oh, I don't know. Maybe to pass the test? Ooh, and maybe someday, just maybe, you'll find out that it's actually kind of useful. And you'll be like, whoa, Mr. Krause, a genius. And then you'll know the true power of Brugger's coffee and exponential logarithm functions. Yay! All right, here we go, kids. We're about to start, but I got to pause for just a second. I'll be right back. You won't even notice the difference. See, you didn't even know I was gone. Ooh, I need a little refreshment. All right. So anyway, I'm gonna have a link to this video right here to a guy's video on YouTube. I'm not gonna show it on my video because that would be kind of like stealing. So I don't really want to do that. Plus one video inside another video, that'd be kind of weird. So maybe I'll just put a link in if you want to watch it. But what it is an experiment. If you were in class, you saw this experiment. We showed it in video. And that is a guy set up 225 mouse traps with ping pong balls on them. And then we have Matthew. Here's Matthew. Matthew comes in, and Matthew puts one ping pong ball to start the experiment. So we have one active ping pong ball to start the experiment. Now, so of course, there's 226 ping pong balls in the glass cage. So at the time of the video, at 1 minute and 33 seconds, there was one active ping pong ball. Half a second later, that one ping pong ball hit one. You gotta kind of imagine it just can only hit one ping pong ball and get that to explode. So therefore, we have two ping pong balls going, and then those two ping pong balls go and only hit two. You're gonna pretend like it can't go in the middle; that it can only hit two. And now we have four going. And then those four hit four more, so we have 8 going, and so on and so forth. Of course, until the experiment ends, we just keep doubling. Every time we double, because every single ball hits one other ball, and now you have 2 balls in the air. So each one doubles itself. So 128, but of course this one has to be 226, not 256. I know you want to make it not 256, but it can't be 256. By the way, these notes can be found at mrkrausmath.com. Look for Unit 6, Day 1. And if you haven't hit the subscribe button, hit that too. The reason it can't be 256 is because there's only 226 balls in the cage. Again, watch the video if you want to see what the heck I'm talking about. So what we're going to do is we're going to plot these values. So at time 0, basically, or when this experiment starts, we have 1 ping pong active. Then we have 2 active. Then we have 4 active. And then we have 8 active. And then we have 16 active. And if you were to graph this function so far and stop there, just stop right there, you might think to yourself, it's got a little bump in it, but that's a linear regression. But should do linear regression on it. And of course, you can't really stop experiments there. That would be stupid. So we're just going to keep going. That'd be 20, that'd be 32, 40, 50, 64, 70, 80, 90, 100, 110, 120, 128. That's 30, 40, 50, 60, 70, 80, 2, 10, 26. All right, so if you stop the video and actually see that I'm off, you'll get over it. I'm half blind, and looking at this thing is just, oh my God, it's painful. All right, so it would look something like that. Of course, if it was really exponential, then we should be up here near 256, which, would take this last piece and go, and you see it starts getting steeper and steeper. So one of the things I did in class, and I got to get my calculator up. Let me get rid of this stuff. Sorry. Don't need any of this stuff anymore. That's for later. That's for later. That's for later. There we go. Get my calculator up. And I guess I'll come back to it. So anyway, exponential functions grow very fast. Oh, I need it up anyway, so for a couple of things. So what we're going to do is we're going to... Now, the nice thing about Algebra 2 Trig is it actually tells you which regression analysis. Now, I say that's nice. It's only nice because it's sort of unrealistic. You know, in real life, what you're going to do is you're going to collect data, put it on a graph, and say, okay, look, let's see what the end behavior looks like. Is it sloping up? Does it slope up on both sides? Does it look like an odd function, an even function? Does it look like a linear function? Does it look quadratic at some point? For some reason, my calculator is not appearing. And then you will have to do, there it is. Then you would have to pick the correct regression analysis. But, you know, the nice thing and the kind of juvenile thing that the Algebra 2 Trig stuff does is it actually tells you. So for the Regents exam, that will be nice. For reality, that won't be so nice. So what we need to do then is create a regression analysis. And then for our purposes, we're going to assume at the end, we had 256 active ping pong balls. So let me leave this over here, and I'll go into spreadsheet mode. And our independent variable in this case was time. Time always has to be independent. I don't think time can depend on anything, right? You can't say, oh, let's slow down time, let's speed up time. That's not going to work. And the dependent variable is ping pong balls. So 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. And 1, 2, 4, 8, 16, 32, 64, 128, and 256. So what we'll do is we'll do regression analysis on this. Just as a reminder, you go into menu, statistics, stat calculations, and don't just be a monkey and pick the one that, oh look, linear regression, I've seen linear regression before, yeah. It's like 4 different accents there. It's pretty good. I know we've done quadratic, done a little bit with cubic, done a little bit with quartic, right? We've done cubic, we've done quartic, we've done quadratic, we've done linear regression of mx plus b, but we don't want any, and we've done a little power regression, but now we don't want those. We want exponential regression. The independent variable was t. Don't pick just pick them in order. Pick the right one. And the dependent of the y list was p. We click OK, and we get a regression equation. Now you'll notice this regression equation, which is right here in this box, doesn't have the y equals, and we should write down what a equals, and we should write down what b equals. So let's get back to that. So the equation is y equals a times b to the x. I would just assume you not write times. I would assume you write it, or rather you write it like this, a b to the x. Because a couple things happen. One is sometimes you think more than one thing gets raised to the exponent, which it doesn't. And a lot of times you'll just lose that dot. So just use parentheses. We said a was 1 and b was 4. So our equation is y equals 1 times 4 to the x, or just 4 to the x. And why 4 to the x? I mean, when I looked at it, I said, why is it not 2 to the x? Aren't we doubling every time? Well, what it is every second we're quadrupling. That second quadrupled, that second quadrupled, so this is 4 to the 1, right, to the 1th power. 4 to the squared power. This is 4 cubed. This is the 256 is 4 to the 4th power. So that's what that is. So in order to bring home or drive home a point about how powerful or how unbelievably crazy exponential functions is, I want to ask you a question. If my GoFundMe page and my donations started to come in, or if Brugger's started to pick me up as a sponsor, a little hint there, buddy, because I'm drinking some delicious burger coffee here. And I had $1 million to give away. Or had I won that 1.3, actually it was 1.6, almost $6 billion. Had I won that, and I had $1 million to give away. And let's say we're in January. And I said to you, look, on January 1st, I will give you $1 million. Or I'll give you a penny every day. And then I'll double whatever you got. So you save it, I'll double it. So whatever you got for that penny and you double it, I'll give you. So $1 million right this second. Here it is. Boom. There it is. You're down. $1 million. Or would you rather take a penny today, and tomorrow I'll give you 2, and the next day I'll give you 4 pennies, and then 8 pennies, and then 16 pennies, and double that, and then at the end of January, I'll stop. What would you take? Well, if you're a smart person, you'll take the $1 million right now. And the only reason I say that is because who the heck knows? Somebody might just get tired of giving you pennies. Or maybe they'll run out of pennies. Or maybe they just lose you. Or maybe they stop doing things. At least $100 million is for sure thing. But if you know that that person just won the $1 billion lottery, and you're like, okay, give me that penny. Now I want you to double it. Times 2. Now I got 2 pennies. So that's day 2. Day 3. Day 4, 5, 6, 7, 8, 9, 10. Would you change? Because we're only up to $5, and we're a third of the way through the month. 1/3 of the way through the month. You only got $5. 10 days in. Change your mind? I'll give you $1 million right now. Change your mind. No? All right. 11, 12, 13, 14, 15. 15 days. We're halfway into the month. You got $100, $150, $160. You don't got anything. I'll give you $1 million right now. Change your mind? Would you? Maybe. Getting nervous, though, aren't you? 16, 17, 18, 19, 20. All right, 20 days in, you got $5,000. Now, let's think about that. Had I taken the $1 million, I would be $995,000 ahead. $995,000 ahead. That's a lot of money. Take it now. We're on day 20. There's only 10 days left of the month. Come on, take it, take it, take it, take it, take it, take it! Burgers, coffee. All right, let's keep going. 21, 22, 23, 24, 25. 26. 27. 28. 29. 30. 31. Holy crap. $10,737,419. $1 million. Had you taken the guaranteed $1 million. 1, 2, 3. 1, 2, 3. Boy, that pen is working beautifully. Oh my goodness. I just put a new battery in the thing too. Thought that was going to be the problem. Or, had you taken it the other way, you would have ended up with 10,737,418. Good thing it was January. Got an extra $5 million. Oh, look at that. 5, 1, 4, 7, 3, 7, 9. You just made a $9,737,415 mistake, bro. Exponential functions grow so fast. So if you get a chance to get your money in to an exponential growth thing, do it. But it's all going to be BS. All right, so let's take a look. We got a long video ahead of us, so pay attention. Parent function. The parent function, the new parent function that we're going to learn today is y equals b to the x. Now, I've got 2 functions below here that are y equals b to the x. This one and this one. And yet they look sort of different. This one's going up and this one's coming down, and yet they're the same function. And they are not reflections of each other. They are not reflections. There is no transformation that's being done from this one to get this one. So they are, in fact, just exponential functions. Or just, yes, exponential functions. Now, you'll recognize it as an exponential function when the variable, that's this thing right here, is an exponent. This is a constant, b. It changes, like in our example above, our base was 4, but our variable was x. So as long as the variable is x, we're in an exponential function. So why are they vastly different? This one over here is growth, exponential growth. This one over here should be obvious that it is exponential decay. It's coming down. So growth versus decay. Well, if I remember correctly, our equation is y equals b to the x. And let's say I plug in 1 for this equation. What I would get out if I plugged in 1 was 2. So if I plugged in a 1 here, I would get 2. Well, the only way to do that is if b is 2. So this actual equation that of this thing that's being graphed above is y equals 2 to the x. Let's see if that's true. When I plug in a 2, I should get 4 out. 1, 2, 3, 4. So this is the 0.24, and yeah, that's what I get. Okay, so that makes sense. So in this case, my b was 2. Let's go take a look over here. Again, we have y equals b to the x here as well. But this time when I plug in a 1, I get a half. So that would lead me to believe that y equals, or b equals 1/2 to the x. And again, if I plugged in 2, I should get a 1/4. And that kind of looks like a 4 somewhere around there. So that looks like it's about right. So if I look at it now and I think to myself, okay, so if this one here, the b value was a 2, and this one on the right, the b value was a 1/2, maybe in order for it to be growth, b has to be greater than or equal to 1. And then over here, maybe b has to be less than 1. Well, let's take a look and investigate if b was 1. If b was 1, we would have the equation y equals 1 to the x. So that would be like y equals 1 to the 1, or y equals 1 squared, y equals 1 cubed. Is that going to change value? What is 1 squared? 1. 1 cubed, 1, or 1 to the 1 is 1. 1 squared is 1. 1 cubed is 1. 1 to the 4th is 1. So we can't actually have a base of 1 because that really just makes it one horizontal, straight, linear line, and that's not really going to give us any growth. I mean, if I tell you, look, man, your money will earn, your base will be 1, you'd be like, oh, okay, wait a second. I'm not going to earn any money. It's just going to stay straight forever and ever and ever. It'll be straight. So we don't want that. We want 1. So as long as it's even slightly bigger than 1, we will have growth. And we also can't have 0 or negative. Because think about it. 0 to the 1, 0 squared, 0 cubed, 0 to the 4th, you're at 0. You can't grow or decline from 0. It's just 0. You're not going anywhere. So we will always, so in order for it to be decay, it has to be a fraction that's between 0 and 1, or a decimal between 0 and 1. And in order for it to be growth, it has to be greater than 1. It could be 1.000000001, which is like kind of like what your banks give you for interest rate, approximately. Unless, of course, you're rich. But it's growth. So that's it. So there's our parent function. Now, we'll talk about what this a is in a minute. But exponential growths have this regression equation right here. All right, so let's talk about this weird thing. I got to move it over. I don't know why I have that over there. So let's move this over. And blow this up a little bit. I'm going to try that. Blow it up. Yeah. Get away from my big fat head. So here's our new function. Y equals e to the x. E. Sometimes it's known as Euler's numbers. And it's Euler, E-U-L-E-R. But since he was a famous mathematician, and it is actually a person's name, I probably ought to count E. And here's a guy that discovered that through multiple experiments, whether it be money or things that occurred in nature or just things that occurred naturally. And maybe I'll leave a link in the show notes to a Wikipedia page or another guy's page that talks about why Euler's number is really, really important. One is it's its own derivative. That's a weird thing. So when you get into pre-calc and calculus and you start taking the derivative of the e function, you'll find out the derivative of e is e, and you'll be like, whoa, that's weird. It is weird. But it also is a pretty important number. And if you do some experiments someday, you'll eventually find out that it's equal to 2.7. Let's take a look. I don't remember exactly. I think it's 2.71828 or something like that. So let's take a look. If I'm right, that's pretty good. So let's graph. What we're going to do is we're going to graph this function. We're going to graph the function e to the x. Now, I'm not talking about this e down here. That's just a letter e. It is not Euler's number. It is not a base that we're talking about. We're talking about this e right here. It's right next to the 1, a little bit over. I'm over here in this area right here. E. I'm going to click on E. So now you see it says, okay, what do you want as an exponent? Well, this is an exponential function, so we certainly want x as our exponent. And we click enter, and we see that we get a growth equation. There it is, our growth equation. e to the x. Now, as before, when I wanted to find out what the base was over here, I looked at when x was 1. When x was 1, it was 1. Now, by the way, do you notice that they always go through this point 0? 0, 1, we'll talk about that in a minute. But so I'm going to do the same thing here. I'm going to go to my table, Control T, and I want to look at my table at 1, and look right there. There it is. Euler's numbers, 2.71828. Oh, 82818. So 7182818. Now, what I want you to remember is that E is approximately 2.7. Approximately. Okay, so someday in life you'll know that they're, but it's bigger than 1, right? So that means we're going to have exponential growth. So as we look at this graph, it seems like I've gotten smaller for some reason, so let's look at it. Let's blow it up a little bit. As I look at this graph, first of all exponentials go through this unless they have a dilation. If they have a dilation of that's bigger than 1, it'll go up. If it's less than 1, it'll come down. But if there's, and the reason for that is if you put 0 as an exponent, plug in 0 to any exponential function, b to 0. I don't care what b is. If anything raised to the 0 power is 1. So it will always go through there, of course, unless I have a dilation or an a value in front. And then it would be whatever a is. But in this case, we're just using e to the 1. So we're gonna graph that. And we said that at 1, it was 2.7. So that's right about there. And so all exponential functions, they can't be made negative. So it's going to grow way like that. It should be close to 9, right in this area around 2. Okay? So let's talk about its domain. Domain, it will go forever and ever to the left. And it will go forever and ever to the right. So the domain is all reals. And the range, notice it will never go below the x-axis. And if you think about it, if you've got the function y equals b to the x, even if I made negative exponents have nothing to do with being negative. Remember, if that was, let's say that was -1, well, what I would have is b over 1 over b to the -1, or, excuse me, 1 over b to the 1, or 1 over b squared, or 1 over b cubed. But that just makes it a fraction, not a negative number. So it will never be negative. And it could never be equal to 0 because there's no way for that to be equal to 0. So my range is 0 to positive infinity. And really, I want you to remember that it approaches the x-axis asymptotically, and it goes forever and ever, very, very quickly up. And then let's take a look at its domain of the inverse. Now, in order to find the inverse, the first thing we're going to do is recall a fact that we learned earlier, and that is that inverses are really just a reflection over the line y equals x. Let's see, that's 1, 1, that's 2, 2, there's 3, 3, there's 4, 4. I know it's slightly off, 5, 5, 6, 6. It doesn't look like that, but remember, this is -1, this is -1, so you got to use the actual points. So we got inverses, if you recall, are reflections over the line y equals x. So this equation up here is y equals e to the x. And we want to do its inverse. So this point right here is 0, 1. So I want to do 1, 0. Let me do it in a different color. That would go through 1, 0 here. This point right here was 1, 2.7. So I'm going to go 2.7, 1. And then somewhere around 8.5, 2, somewhere around there. And then so now we're going to approach the x-axis, and we're going to go up this one. And that is the inverse of the exponential function. So this is, excuse me, I should have called this g of x. So this one down here would be g inverse of x. And for future purposes, what you're going to find out is the inverse function of the exponential function is the natural log of x. Ooh, logarithms, kind of exciting. All right, let's take a little trip back to memory lane, and we remember that just as I switch these 2 points here and here, domains and range changes. So the domain of the function becomes the range of the function becomes the domain of the inverse. And the domain of the function becomes the range of the inverses. And let's see if that makes sense. This is going down forever and ever and ever this way, and up forever and ever this way. So yes, range is going up and down forever and ever, but it starts here at 0 and only goes in this direction for domain. So yes, that makes sense. This thing, don't get scared about that. We'll talk about that later. The natural log of x. Now we're going to look at the most basic exponential graph, and that's with a base of 10. So plug in 0, you get 1. Plug in 1, you get 10. Plug in 2, you get 100. We're not getting there. Plug in -1, you get 1/10. Now think about it. That's 10 to the -1. That's really 1/10. Plug in 10 to the -2, and you get 1/100th, and so on. So it gets really small really fast. So let's graph it. I can't even believe I hit that point. Boom, boom. And then it's going to go really slow, but it will never cross the x-axis. And one of the things I'll be looking for as you graph these things is that you do not pass the asymptotes. All right, 1, 0, 0, 1. So let's go here. We're going to go, and then we've got 10, 1. Doing the inverse here. So remember, it's going to approach the the y-axis asymptotically, and somehow I got to get down. So this is f of x, which is equal to 10 to the x, and what we're going to find out, this is f inverse of x, and this is equal to log of x. Now, one thing that I'm not writing in here, and I will eventually, is that it's log base 10 of x. See, the bases have to be the same. Base and base. Okay, domain and range should be pretty obvious. The domain here is -infinity to +infinity. That becomes the range of this one, -infinity to +infinity. The range of this one is obviously 0 to infinity. And that's only because we haven't done any transformations on this either, right? Don't forget about transformations. So this would be 0 to also infinity. What's this one? 2 to the x? 2 to the x. Okay, so it's kind of like the one we did before. We plug in 0, we get 1. We plug in -1, we get a half. We plug in 1, we get 2. We plug in 2, we get 4. Hopefully that gets fixed. We plug in 3, we get 8. What are you noticing about this function? I hope you notice about this function. Do you notice it's growing a lot slower? By 2 on the other function, I was already at 100. This one I'm only at 4. So this base really determines how fast your exponential function is going to grow. Let's graph its inverse. I'll do it in blue. That would be 1, 0. That would be 2, 1. And that would be 4, 2. And that would be 8, 3. And a half, -1. So this is y equals 2 to the x, and this is log base 2 of x. And they are inverses. So exponential functions and log functions are inverses of each other. Now the cool thing is sometimes you forget about that. So let's take a look at your calculator. If you take it, and what we've done here is I've blown up this part of your calculator right here. This part right here. I've blown that up on the sheet, and you'll notice that exponential and logs are really on the same button. Remember, these are just controls away from each other. The square and the square root. The 10 to the x and the log button are on the same button. And that's an easy way to tell what's the inverse of what. And just very quickly, let's go through these. What's the inverse of squared? Square root. What's the inverse of square root? Squared. What's the inverse? What's the inverse of the exponential function? That's the natural log of x. The inverse of this is log of x. And the inverse of this is log base 2 of x. Now, on each of these, this one here, I did not put something in. This is the natural log of x. But notice I didn't put the base in. The base is e. Because remember, the natural log is the inverse. When I do inverses and I get my kids all confused and flustered, I drink Brugger's coffee. Those of you sitting at home going, what the heck are you talking about? Grouse. Oh, I choked on my coffee. The natural log of, oh, this is not natural log. This is the log of x. It will become more obvious to you as we work through these, log of x. But again, I didn't put the 10 in. In this one, I had to put the 2 in because it's not the common log. This is the common log where the base equals 10. I know my head's probably in the way. Base is 10. This is the natural log. And it's got a base of e. Okay, the base is e for the natural log. And you have to remember that's because that e number is a number that occurs naturally in lots of different venues and things in life. Okay, so let's go through these quickly. We're just going to graph these. Remember that this is not going to ever be negative, so I shouldn't see this cross the x-axis. This is exponential growth, and it's growing pretty fast. I really just want to see that you understand it's growing pretty fast. Because my base here is a half, I know that this is exponential decay. It's always going through the point 0, 1 and does not cross the axes. So over here, e to the x was, let me just draw an e to the x. This was e to the x. Now the negative in front is a reflection. So we would use our calculators to do these. We're going to use our calculators in class. It's just a reflection over the x-axis. And if you remember correctly, so in this case, the answer to this question is right here. This one. I'll do the dotted line, which is the actual, and then I'll do the reflection. So if you remember correctly, the natural log went like this. So if I reflect that over the x-axis, that would go, oh wait, it would do this. So this is the negative natural log of x. 2 log x. Well, instead of going through 1, we're going to now go through 2. Well, instead of going, through 1 here, we're going to now go through 2 here. So it'll be the same function, but it's got a 2 in front. So instead of going through 1, 0, it goes through 2, 0. This one, we've just modified the exponent, but it's still, when x is 0, we're going through 1, and it's still exponential growth. No big deal. All right, let's move on. The domain of the logarithm function goes from 0 to infinity. We've discussed that before. And the range goes from negative infinity to positive infinity. Okay. It will never cross. I know it looks right there. It looks like, hey, you're hitting the axes. But if you blew that up, you'd see that there's just a teeny bitty space in between there. Teeny bit of space. Something did not. Maybe am I too blown up? Maybe I gotta unblow up. What happened here? That page did not come through. Oh man, that did not come through. That's supposed to look like, I think, is this the natural log? This is day. Cool drive. Oh, no, so I want to do. Ba-doom. Day 2 notes. Somehow, oops, day 1 notes. Didn't like switching back. All right, so all I did was show here, and I don't think can I pen on this thing? Why can't I not pen on this thing? Layout, design. I thought I could pen on this. Hold on, let me pause for a second. I don't know what you're watching me. Yeah, it looks like I can ink on a Word document. So maybe what I'll do is take a look at this one. I probably should blow this up a little bit though. So over here, we already talked about the domain and range. And this is the natural log function. You'll notice that it's very difficult to tell the difference between the natural log function and the actual log function. They're basically the same thing. The only difference is this one has a base of 10. And this one has a base of e. That way at 2.7, we should be at 1. There it is, 2.7 at 1. And at 10, which is over here somewhere, we should be at 1. So let's just take a look. I'm going to go back now. You'll notice that these two things are basically the same. This is the exponential function. This is the exponential function. This is the logarithmic function. I wonder why that didn't print out well. Where do you go here? I hope the next, wait. This next page? I think it's because I'm flipping back and forth between landscape and not landscape. So I'll come back to that one. So anyway, transformations. This is, and this will be true for this one as well, so I'm not going to even bother to go through it. This is a reflection. This is in the x-axis. This is, the A is a dilation. Now again, a dilation could be half or 2. It's going to grow or not. This is just the base. This is a translation, left or right. Remember, that one's backwards. And this is a translation, up or down. And then up or down normal. And if I go take a look at this document, it's the same thing. Reflection, dilation, there's my base. That's a movement left or right, and that's, see, working in Word doesn't work very well. And that is a translation or a move up and down. So let's see what we can get through. I'll get through just these then. So let's see what we got. We've got a dilation of 2. We're going to move to the left 1, and we're going to move down 3. We have a dilation of 3. And don't worry about this one. And this one is growth. This one is decay, because it's got a 2/3. It's less than 1. We're moving left 1, down 3. This one, we're going to move to the right 2. This one has a reflection and up 2. Dilation of a half, left 1. Dilation of 3, right 2. There's probably more to it than that, but I can't really see those papers, so don't worry about that. I think we're going to get that. I think we've done a good enough job with that. So we're going to evaluate and compose functions, and really all I'm going to do is show you how to use the calculator to do this part. This part should be rather quickly. You'll notice that on the calculator, why can't I graph? My pen dying. I think what's happening is my computer's dying on me because I've been going too long. I hope I've been recording. Yes. I don't know what that thing was. The display driver stopped and is now recovered. Well, thank you very much. It stopped and now it's recovered. So hopefully we're working. So the functions that we're going to deal with are going to be e to the x, this exponential function, this log function, and this natural log function. And those buttons can be found very simply on your calculator. So this is really just f is e, so this is e to the 0. Now I don't really necessarily need to put that in my calculator, but I'm going to. But e to the 0 I know is 1, because anything to the 0 power is 1. Why I did that? So if I go to my calculator and I go into calculate mode and I type in e to the 0, I will get 1. Pretty simple. G is 2 to the 3 minus 1 plus 3. So 2 raised to the, 3 minus 1 plus 2, I believe it was, right? And I get 6. H is the log base 3 of x. Now log, in order to get log, you see it's right here. It's above the 10 to the x. You have to hit the control button. Control log e, and we had base 3. So first thing I'm going to do is put in the base. And the number was 1. And this one should come as no surprise to you. It's 0. Because, remember, inverses switch. So if I had 3 to the 0, that would be equal to 1, or log base 3 of 1, that should be equal to 0. Notice they are inverses of each other. Inverses. K is the natural log. So in order to get to the natural log, I have to hit control this. Notice there's no opportunity for base. That's because this base has to be E. It can't be anything else because it's the natural logarithm. So there's no reason to put in a base. There's no reason to give you an opportunity to put something in there stupidly. -7. So -7 plus 1. Now this, or plus 8. This should come as no surprise to you that this is also 0, right? Because really what you're doing is taking the log, or the natural log of 1. Well, the natural log of 1 is 0, because all log functions go through 1, 0. All exponential functions go through 0, 1. Let me say that again. All exponential functions will go through 0, 1. And all logarithm functions will go through 1, 0, unless there is a transformation of some type. Now we're going to do composition of functions. So all we're going to do is f of g of 1. Did I do g of 1 yet? I have not. G of 1. Let's see if I can figure out what g of 1 is. G of 1. Well, that's going to be 1 minus 1, which is 0. 2 to the 0 is 1. So 1 plus 3 is 4. Now, I could put that in my calculator. You know, I could do it a couple different ways. I can take 1, and I can stow it into x, and then type in 2 to the x minus 1, 2 raised to the x minus 1, plus 3, and I'd get 4, blah, blah, blah. And then I'm going to do f of 4, right? Am I doing f of 4? So e to the 4. E, notice, and then really what I'll raise it to is that thing. So, and we get 54.598. 54.598. I'm only going to do one more of these. We're going to practice these in class, and if you don't have a calculator, watching me do these things is kind of stupid anyway. So this is f of h of 3. So we need to do h of 3. So our x value is 3. So h is the log base 3 of 3. Now this is going to be kind of interesting. Control log base 3 of 3, right? Isn't that what it is? Enter. 1. Weird. 1. So now we're going to do, this is really equal to f of 1. Well, f is just the e function. So this is equal to e to the 1. And we know that e is 2.7. What did I tell you to round to, by the way? Hundreds place. Oh, it's 2.718, so 2.72. You don't believe me, we come over here, we hit e to the 1, enter, 2.718, round to the hundreds place. All right, so I'm not going to go through all these things. I mean, that's just kind of silly. We'll do those in class. I could be here all day on these things. Well, let me hold on. K to the 100. What's k to the 100? Nah, that's boring. All right, so those are all boring. But anyway, that's it. That's a little introduction to logarithms and exponential functions. Right now, all I want you to understand is exponentials and logs are inverses of each other. The natural log and the e function, or the e base, which is the Euler's number, if you want to call it Euler's numbers, they are also inverses of each other. I want you to try to remember that e is about 2.7. For now, that's about all I want you to know about that stuff. And I want you to know that exponential functions grow very, very fast, and logarithmic functions are their inverses, and they grow very, very slowly. And that's it, kids. Day 1. Bodied. Yes, hit the subscribe button, hit the like button, hit the donate button, hit the commercials if those suit your fancy. Just click them on a few that only suit your fancy. Don't just keep clicking on them. That would be stupid. All right, guys. You guys are awesome. You rocked it out today. Nice job. Catch you on the flip side. Bye.